All right, so now we're going to talk about systems, and systems are a huge importance, especially College Board. They love to talk about systems of objects, and that's super critical. So let's talk about what we mean by systems. Now, there was sort of an implicit choice of what we include in the free body diagram so far. So for example, if I draw a free body diagram of myself here, okay, and we do the mg for gravity, we'll say like, well, what do we include in there? Do we include my shirt, my watch, my hair, right? They all have their own masses. Why is it we get to include some of these other objects? Like, why do I include my shirt? If I take off my shirt, does that my free body diagram change? And if so, why? So why is it we say, because we're made up of cells, fingers, all these different components. Implicitly, we're saying, yes, when we drew the free body diagram, it includes all of them. But why? Does the universe care what we define mathematically when we are doing our free body diagrams? Not really, actually. The choice of what we say is in the system is completely arbitrary. The universe doesn't operate on saying like, oh, look, Alan is attached to, his fingernails, so we're going to include that. So when the Earth pulls on it, it's going to calculate the mass of his fingernails and then pull on it. Like, that's not how it works. Just the Earth pulls on everything, and what we choose to include as Alan, right, myself, as part of the free body diagram is a choice that we make when we're doing analysis, but it's not a choice the universe makes, right? It's not like that's not how the Earth decides how much to pull on you. And so it's technically arbitrary. The thing is let's say you let's look at let me go full video here. Let's talk about my shirt here, all right? So I have my shirt here. And if we said like, well, Alan, what if we drew a free body diagram that didn't have your shirt, or just a free body diagram of the shirt by itself? Well, then we would say like, okay, cool. We're gonna have the shirt be a separate object from Alan, right? Not part of our system. So that means if I draw the free body diagram myself, is I have gravity on me, I'm touching my chair or the ground, so that exerts a normal force upwards. But then the shirt is external, right? It's not part of my system, so it's exerting a force on me, and probably like think of it as maybe a simple surface here. Actually, let's just do like a box like this, right? Like I have this in my hand. Okay, so now this box, if I don't include it as part of my system, right, my mg, it's going to exert a downward force, a normal force from the surface here, pushing downward on my hand. And then I'm going to exert an equal and opposite force on this Kleenex box, right, by myself. And so if we include the Kleenex box in the systems, we don't have to worry about the fact that it exerted a downward force and I exerted an upward force. That would be what we call an internal force to the system if I included the Kleenex as part of the mg, the part of the system that we were dealing with. If we said like, okay, Alan, we're going to do a free body diagram of the Alan Kleenex box system, then I would not worry about the force that I'm exerting on the Kleenex and the force the Kleenex exerting on my hand. They would cancel each other out. It would be an internal force. And they cancel each other out by Newton's third law because they're equal and opposite forces. Okay, so the selection of a system, right, comes down to like what objects you include and any internal forces for them. So if I don't include my shirt as part of my free body diagram, as part of my system, then the shirt is an external object that's going to exert a normal force on me. And that's what I feel. I feel the shirt pulling down. That's how I can tell I'm wearing a shirt. That's how my nerves can tell that it experiences that force there. So let's look at an example of how this works. We get to choose what the system is, and we're going to talk about the pros and cons of the system. So we have two blocks being pushed with a force of 5 newtons. The right block has a mass of 4 kilograms. The left block has a mass of 2m, which is 8 kilograms. What is the acceleration of the blocks? Okay, so let's do separate free body diagrams for each object here. That's the classic method. Prior to this lesson, this is what we would have done. So for the 2m block, we would have drawn a free body diagram that looks like this. We'd have 2mg pointing down. And then what's touching it? It's got his rope. That rope is pulling to the right. We'll call that T. And then the ground is touching it. That's an Fn. Nothing else is touching it. So we're done. How about the M block? The M block has mg pointing down on it. What's touching it? We have this rope. It's pulling it to the left. What else is touching it? This ground here is touching it. So this is Fn. We'll call this for M. This is for 2m because these are different normal forces. What else is touching it? This little F here is pulling to the right. Now the acceleration is in the rightward direction. That's what we have to right, and they want to know what the acceleration is, right? And they're both, because the rope is the same length, like the rope's not getting longer or shorter, the blocks move together, they have the same acceleration. So then we're going to do F net equals ma, and we'll just do the x direction because that's all that really matters. We'll say right is positive. So if t is pointing to the right, that's it. This is a mass 2m times its acceleration. And then for this guy, we said to the right, F is pointing to the right, T is pointing to the left. That's equal to M times the acceleration here. And then if you add these two up to get rid of the tension force, because I got to get a number and I don't know what the tension force is, you add these two equations. You get F minus T and plus T cancel, gives 3ma. And so the acceleration is going to be F over 3m. Okay, and I'm not going to plug in the numbers. We'll just leave it like that and symbolically like that. Okay, so I know F, I could plug in 5. I know M is 4, so I could plug in and get a number there if I wanted to, okay? So that is me doing the standard method that we did before. So now what if we said, oh, what if we just consider this entire two objects as a whole system? Okay, so we're going to just treat the whole, we're just going to say, like, look, this F is just pushing on a block that has a mass of 3m. Like, just make it a single object, right? So now let's draw a free body diagram of the system here. Okay, so we have 3 mg, right, because we have gravity on all of the objects, right? And then we don't worry about the rope because that's internal. This part here is internal. The F is external force, though, because that's not part. We're just considering the two blocks as our system. So we have an F pointing out here, and what's touching the ground? You have Fn here, like this. Now, the acceleration is to the right, and so when we do F net equals ma, you have F pointing to the right. That's the only force. We'll say right is the positive direction. And that's equal to 3m times the acceleration. The acceleration is F over 3m, like that. And notice we get the exact same answer, right? A is equal to F over 3m. Now, what did we lose in this process? One, mathematically, it was a lot simpler, right? Obviously, it looks like just way simpler to calculate than this. This required solving a few systems. Wasn't terrible, but definitely, like, objectively, far more work than it was this one. So to find the acceleration, nice, convenient method for doing that. What was lost? If I asked you in this problem, what is the tension in the rope, you are not able to do it. We lost the tension in the rope because we made it internal to the system. So we lost some visibility into what the tension was by doing a free body diagram of the entire system like this, of the two blocks. Okay, whereas here, if I wanted the tension, I would just say like, oh, I'm going to take that, plug it right back into here, and I would have 2m times F over 3m. That would be 2/3 F would be the tension. So some advantage of the other system was to say like, oh, the other way we approach it as separate objects, then we'd say like, oh, the tension was more available. So it depends on what you're solving for, right? And this, in the case of if all I was asking for was the acceleration, then doing the systems approach is going to be a faster way to get to that same answer. Okay. Oh, I forgot. I was going to do two blocks accelerated up an elevator. So let's do a similar scenario here. It looks like I forgot to do it. So we'll just, let's say I have two blocks here. We'll call this M1. Well, M1, we'll put another block on top of it, M2, and they're accelerating upwards with an acceleration A. And I ask you, what is Fn from the elevator? From the elevator onto the bottom block. Okay, like that's the question we have here. Okay, so again, as separate free body diagrams, and let's say the acceleration here is 2 meters per second squared. Okay, so I already know the acceleration. So what is the Fn from the bottom force? Again, if you do the free body diagram separately, it can be a little bit tricky. So for M2, we're going to have gravity. And then what's touching it? M1 is pushing up on it. So this is Fn from 1. Okay. Now, M1, that's everything that's touching M2. If we do M1, we got gravity here, M1g. And then we think about like this guy up here. This is equal and opposite. So M1 pushes on M2. So M2 pushes down with Fn 1, the same equal and opposite forces because M1's pushing on M2. So M2 is pushing down to M1. What else is touching M1 is the ground here, and that's what we're looking for, the Fn. Okay, and then if we say, oh, the acceleration is upward at 2 meters per second squared, right? And we'll just use A. Then we'll make up positive for all of these. So when I do F net equals MA, then you're going to get Fn1 is pointing up, M2G is pointing down. That's going to equal M1 times the acceleration, or M2 times the acceleration, excuse me, because that's the mass of this free body diagram. M1, when you do F net equals MA, you have Fn pointing up, you have Fn1 pointing down, you have M1G pointing down, and that equals MA, the mass of this free body diagram, times its acceleration, right? Just like we do F net equals MA. And if I want an answer for this Fn, I can just put this one underneath and add them up, because the normal force will then cancel. So you get Fn minus M1G minus M2G is equal to M1A plus M2A. Got to add those up. And then the Fn would equal adding them all up. M1A plus M2A plus M1G plus M2G. And notice, like, the A and the G, like, you can group them up, right? This factor out an A, you get M1 plus M2, just mathematically. Factor out a G here, you get M1 plus M2. And then now you could factor out an M1 plus M2 and get A plus G. Okay, so that would give you an expression for the normal force. Okay, so that is separate objects. Now, let's just treat it like a system. Let's say all I care about, because I just care about this force, let's treat this entire object as a single system. It's an M1 plus M2 system. Okay, so we draw a free body diagram. You have gravity of this entire thing, M1 plus M2. And then you have a normal force from the ground. And you ignore any of the forces between them because they're internal. They're now all part of the system. So any actions between M1 and M2 are negated. They are ignored. And it's mathematically, it's because they're equal and opposite. They're just going to cancel each other out. Here, you know, the acceleration is upward at 2 meters per second squared. So then if you do F net equals MA, we say up is positive. It's going to be Fn minus M1 plus M2 times G is equal to the mass of this free body diagram, MA, M1 plus M2 times A, and you can just add them up. And notice we get the same answer, but a lot more simply, right? So there's going to be a lot of advantages to then combining objects as a system. The choice, we're going to get the same answer. It's mathematically it comes out the same, but the choice will allow it to be simpler. One, mathematically simpler to do with some scenarios, and then two, it may be conceptually easier to understand what's happening in a problem when we group them up in the system. So very frequently, okay, College Board AP questions ask you, they tell you what the system is, and you got to treat the correct way to look at the free body diagram and everything by having the correct treatment of the systems, okay?